Welcome to a screencast on an introduction to resonance. And we'll start by taking a look at the nitrate ion, NO3-. And let's draw its Lewis structure. And first we note that nitrogen has 5 valence electrons. Oxygen has 6 valence electrons, but there's 3 oxygens, so that's 18 more valence electrons. And then it's a negatively 1 charged ion, so it has 1 more electron. And so the sum total of electrons in this species is 24. So we'll put the nitrogen surrounded by 3 oxygens, and we'll start filling in the 24 electrons for this species. So that's 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And notice we had to make a double bond to be able to get an octet around each oxygen and around the central nitrogen. And there's the Lewis structure for the NO3- ion, and we actually, the way we write these ions is we put brackets around it and then a negative charge to indicate that the whole thing has a -1 charge. And now it's important to note that this NO3- ion, how we drew the Lewis structure, and so here we have it where we've shown lines to represent the bond. So we had a single bond, and a double bond. And this is an example of something that is known as resonance. And resonance is when you can draw 2 or more valid Lewis structures for the same molecule. And if you had drawn this out, it's possible you drew the double bond to the quote-unquote right-hand side oxygen or to the left-hand side oxygen rather than to the top oxygen. So you might have drawn this or you might have drawn that. And all of these are valid Lewis structures for the same molecule, in this case for the same ion. Always have an octet around each oxygen, always have an octet around nitrogen, but the double bond could be in 1, 2, or 3 different locations, or one of those possibilities. Okay, well, it turns out that the real molecule has a number of ways that we can represent it. And one is to draw all 3, in this case, of the possible what are called resonance structures. So the double bond here, the double bond there, or the double bond there. We draw all 3 of them, and then we put arrows, double arrows, between each of the possible structures. And this is one way that we can represent that. Now, that's kind of a pain because we have to draw 3 separate structures in this case. We can also note that if you analyze this molecule, its actual structure isn't a double bond, single bond in any particular arrangement. In fact, all of the bonds are identical to each other. The actual structure has 3 equal bonds. Each of them is stronger than a single bond, but weaker than a double bond. Each of them is shorter than a single bond, but longer than a double bond. And the actual structure, in this case, is an average of these 3, what we call resonance structures, with each nitrogen-oxygen bond being approximately 1 1/3 of a bond, and all the bonds have the same bond length. And where we get the 1 1/3 bond is by noting in any structure there's 1, 2, 3, 4. So there's 4 bonds surrounding the nitrogen, but they're split among 1, 2, 3 locations. And this is the case for all of these 3 resonance structures. So this is like 4 bonds in 3 locations, or about 1 1/3 bond in each location. So here's one way we can draw it, all 3 resonance structures with double arrows in between. We can also draw a line and then a dotted line representing more than 1 but less than 2 bonds. So this is representing 1 1/3 bond, 1 1/3 bond, 1 1/3 bond. And note we're not showing the lone pair electrons because those are also evenly distributed and it's hard to show the arrangement. We can also do a ball and stick model, and this shows equal bond length between nitrogen and each of the 3 oxygens, and of course equal bond strength. And we can do a space-filling molecule as well, and again representing that all 3 nitrogen-oxygen bonds are equal to each other in terms of strength and length. Now, this is kind of a weird concept, takes a while to wrap your head around it. And by way of one possible helpful analogy, if you have a horse and a donkey mate with each other, when they do this, they actually form something known as a mule. And a mule can be thought of as sort of a horse-donkey hybrid that's more or less half horse and half donkey. And important to note, it's not alternating between being a horse and a donkey. It's permanently half of each. And that's the same that applies when we look at these resonance structure molecules. They do not have bonds alternating between being single and double. They are permanently, one in the case of nitrate, 1 1/3 bonds in each case. So that's the basic ideas of an introduction to resonance.